My name's Jerome Malla. I'm a neuroscientist and MRI clinical science specialist for General Electric Healthcare. So for about the last 15 years, I've been focusing on advanced MRI, specifically diffusion imaging in the context of concussion, or what some people call mild traumatic brain injury. So from the GE perspective, it all started with the GE NFL Head Health Challenge. It was a $100 million US partnership, and it was an open innovation challenge to study mild TBI. The challenge 1 was methods for diagnosis. Challenge 2 was the mechanics of injury. Many submissions and hundreds of subjects were scanned, mostly sports people, football players, and healthy control subjects. A major outcome was the development of new MRI technology with a focus of detection on mild TBI, and this led to the GE Signa 3 Tesla Premier. So the developments are focused towards a study of concussion. It has to have a higher gradient amplitude, as this equates to a higher resolution whilst maintaining signal-to-noise ratio. It also has to have a wide bore opening, as the person has to be comfortable without the feeling of being confined. The hardware was completely redesigned to provide this higher gradient strength while also reducing its heating. By using this new hollow, water-cooled gradient design, the MR scanner is far more efficient and can maintain homogeneity for longer exams. This new technology is particularly important for the study of concussion, where damage is likely to be neuronal microstructure. That is, the new technology can provide images of very high resolution, and it can do it fast. Typically, brain MR scans of people suspected with concussion do not show anything clinically significant, and that's because the damage, if present, is likely to be smaller than what we can see on the scan. So by imaging smaller voxels, that is, higher spatial resolution, we can see the brain in more detail. You can use Hypersense, compressed sensing, higher resolution in a shorter amount of time. Here's an example of using Hypersense on a 3D time-of-flight, which we call a TOF. This is using our newly developed 48-channel dedicated brain coil. If there are very subtle regions of microscopic damage, then these will be detected using this combination of advanced hardware and software. These data were acquired using the whole brain 48-channel air coil in a Signa Premier. DTI is a technique widely used to investigate whether there is any damage to microstructure after concussion. Here's another example. Note the very high level of detail and contrast, with the white matter going right up to the grey matter gyral crowns, as we can see in this image here. We can measure parameters such as flow, vessel diameters, pressure gradients, speed, and essentially this can be achieved in a single scan. So if there are cardiac implications as a result of concussion, then they are likely to be detected using this technology. Here are some visual examples of 4D flow. We also have a compact 3 Tesla MRI scanner. Head only, extremely high slew rate, which means faster scans with less noise. Only 12 litres of helium, so no quench pipe is required. The gradients are 80 amplitude and a huge 700 slew rate. It's very light as well, and it's easy to sight. This is a very high resolution DTI, 273 directions at 3 different B values. This is a very high resolution scan. So if there is microstructural damage to white matter fibers, which are often stretched and therefore damaged as a result of concussion, then this is likely to be detected using this technology. This really is a breakthrough in image quality. Using deep learning, the technology recognizes true signal from a noisy signal and uses only the true signals for image reconstruction. This new technology is particularly important for the study of concussion, where damage is likely to be neuronal microstructure. That is, the new technology can provide images of very high resolution and it can do it fast.